Hey everyone, and welcome back to the Foundry by Forge College. Let's dive right in, shall we? In our previous lesson, we really unpacked royalty calculation strategies. Well, today we are shifting gears to tackle a massive engineering hurdle in Web3 integration as part of our Web2 Solana Integration Foundations module. Our topic for today's explainer: designing data exchange flows. More specifically, we're going to look at how we take wildly unpredictable, messy Web2 data and translate it into the incredibly strict, deterministic inputs that the Solana blockchain absolutely demands.
So think about it. Web2 JSON is famously loose. It's flexible, sure. Sometimes a date format is beautifully constructed, and other times, honestly, it looks like someone literally sneezed on a keyboard and the Web2 system just kind of shrugs and accepts it anyway. But Solana is like the absolute strictest bouncer at the most exclusive club in town. It only accepts strict bytes, deterministic formats, and fixed layouts. If you don't match the exact expected byte structure, there is no way you're getting in. Your transaction just gets flat out rejected.
To get past that bouncer, we're going to build a data assembly line. Here is our agenda for the day. 1. The gap. 2. The blueprint. 3. Normalization. 4. Serialization. 5. The e-commerce schematic. And 6. Action endpoints. Let's get to it.
Starting with Section 1, the gap, Web2 chaos versus Solana order.
Knowing what you want your smart contract to do on-chain is actually entirely useless if your systems can't speak the exact same language. Field-level mapping and deterministic serialization are the absolute core tasks when moving a Web2 JSON payload into a Solana instruction format. This is the unbreakable contract we are creating today. We're establishing explicit, ironclad rules for every single piece of data moving from a web browser to the blockchain. There is zero guesswork allowed here.
Moving right along to Section 2, the blueprint, the 3 pillars.
I want you to think of your API bridge as a literal physical factory assembly line, and it's got 3 major stations. Step 1 is mapping, which is basically just drawing lines from incoming Web2 fields over to our target Solana fields. Step 2 is normalization. Think of this as the car wash station. This is where we scrub and clean all that messy data. And finally, Step 3 is serialization. This is where we meticulously pack that clean data into highly specific boxes so the network validators actually accept them. This flow right here, it's the beating heart of any Web2 to Solana bridge.
Which brings us to Section 3, normalization, cleaning the data. All right, let's tighten the bolts on our data with some everyday examples of normalization. For instance, we might receive a dozen totally different time formats from a client, but we must strictly convert all of them to UTC ISO 8601. Also, we never ever send floating point dollars. We always convert them into integer cents. We strip out weird dashes and we enforce lowercase IDs. The golden rule here: normalization must be pure and idempotent. It needs to be a side effect-free car wash that produces the exact same pristine result every single time, no matter how many times you run that identical data through it.
So that actually brings up a massive question. We've mapped our fields and we've washed and normalized our data, great. But how do we actually ensure the Solana RPC node accepts our perfectly packed box every single time, without fail?
That takes us to Section 4, serialization and idempotency.
Okay, this is where we stop dealing in abstract concepts and lock in our exact byte structure. But before we pack the box, let's really define idempotency. Basically, it means producing the same deterministic output regardless of how many times you process the exact same input. Think of the classic elevator button joke. You press the call button, right? And then, because you're impatient, you smash it 5 more times hoping the elevator comes faster. The elevator system is idempotent. Pressing it once or 100 times does the exact same thing without crashing the entire building. Well, your data bridge has to act the exact same way.
For the actual packing process, which is serialization, we generally have 2 approaches. First, you have structured serialization, like canonical JSON, which is fantastic for Web2 testing and readability. But then you have binary serialization, using formats like Borsh or anchor layouts. This is highly compact, and it's exactly what on-chain programs expect to see. Mastering these specific binary layouts is actually a really big part of the deeper technical courses in API development at Forge College, mostly because getting the bytes wrong is literally the #1 reason transactions fail.
Section 5, the real-world e-commerce schematic.
Let's move from all this theory to a really concrete example to see how it comes together. Imagine you're integrating an online store with a Solana-based order tracking program.
We take the Web2 order_ID, we map it to order_ref, we force it to lowercase, and truncate it to exactly 32 bytes. Simple enough. Then we take created_add, which, remember, could be any weird text format under the sun, and we squash it perfectly into Unix seconds as an unsigned 64-bit integer. We sum up items.price into a deterministic total_sense integer. We even take the text of items.skew and hash it using SHA-256 down to a U64 number. The point is, every single Web2 field is deterministically mapped and converted into a Solana-ready byte.
But guys, here is the real kicker. After normalization, the serializer has to assemble these fields in a fixed order. We're talking buyer_pub key first, then order_ref, then timestamp, then total_sense, then items. The order of these fields is absolutely critical. If your assembly line packs the box in a different order tomorrow than it did today, the resulting binary hash changes completely. Your idempotency is destroyed, and the instruction fails. Order is literally everything here.
And finally, Section 6, preparing your action endpoints.
So, we've walked the whole assembly line. What does this finalized blueprint actually give us? Well, to guarantee a bulletproof, deterministic payload every single time, you just need to internalize these 3 rules. First, keep your normalization pure and idempotent. Second, record your mapping rules as data, like in a JSON file, and not as messy spaghetti code. This makes your bridge fully auditable. And third, enforce fixed field ordering so that identical inputs always produce identical bytes.
Which really just leaves us with one final question for today. Are you ready to build the end-to-end endpoints that actually bridge these 2 worlds? Because in our next lesson, we are going to take all these mapped, deterministic, perfectly packed bytes and actually implement the action endpoints that fire them right into the blockchain. If you want to dive deeper into how this code actually looks under the hood, I highly encourage you to visit forge.college to learn more about the subject and honestly to explore our other Web3 learning modules. It's just an incredible resource. Thank you so much for joining me on this explainer. Stay curious, keep building, and I will see you in the next one.